Hi everyone. In this tutorial on Topologic for Sverchok Blender, I want to show you how you can conduct what we call topological queries, meaning asking an entity in Topologic about its neighbors, about things that are adjacent to it. So as you can see here on the left side, we have built a cell complex. This is a set of connected cells, now represented as a wireframe, just with the edges. But we are selecting a corner cell, for example, in this case, and we are asking this cell to give us its adjacent cells, and we are displaying those in translucent yellow. And as we change the cell, we can get different adjacent cells to it. So this is the other corner, for example, or if we want to go to this one, again, we can get different adjacent cells. So I'm gonna illustrate how to build this from scratch. We're gonna reach at the end of the tutorial this definition, but I'm now going to close it and start building it from the beginning so that you can follow along. Right, so let's go ahead and start a new Blender version or Blender instance. I'm using version 2.92, I think, or 1.92. I'm going to check in a second. This is taking a bit longer than it usually. 2.92, yep. And let's switch over to the scripting layout and switch this over to Sverchok nodes and create a new node tree. And let's go ahead and delete the default cube. So as we've said in different videos, Shift A is usually the preferred way to get to the Topologic menus, and we can create a prism or we can create a prism actually by cell.prism, and we will put it in different locations. Right, so this is the cell.prism, and as we said before, you can feed it either a single origin, a single vertex, or a list of vertices. So we're going to go ahead and use replication in order to create a number of these prisms. So let's go ahead and get a vertex by coordinates. So this is a vertex by coordinates. So the same way, instead of feeding a single x, a single y, and a single z number, we can feed it a range or a list of these numbers. So let's go ahead and get a number range. Here it is. And we can switch this over to count and say we want to go, let's say, from 0 to 3, and we would like 4 of those. Now, why did I do that? Because from 0 to 3, and we want 4 of these numbers, we're going to get 0, 1, 2, 3. That means they are spaced at 1 unit, which is exactly the width, the length, and the height of the prism. So it's a cube, and therefore they will be touching, right? The faces will be touching. So let's go ahead and look at the numbers. Like starting from the number range, if I control click on this one, just to get a temporal stethoscope, as they call it, you'll notice that I have 0, 1, 2, 3. And if I feed these over to the X and to the Y and to the Z, and let's take a look at those vertices, we get 4 vertices. Now, why am I getting 4 vertices? Because I'm using iterate as a replication, which means that it will take one of each list and match them, and then the second one of each list and match them, and the third one and the fourth one, and create a vertex. So let me show you what these look like, these vertices. So I'm going to very quickly put a topology.geometry on them. And then I'm going to control click on this one in order for you to see what they are doing. They climb up, you know, in the Z and the X and the Y and the Z, and this is not really what we wanted. We wanted something that is almost like a grid, a three-dimensional grid. So if we, first of all, I'm going to take out the Z so that you can see it a little bit clearer. So you'll notice that, you know, they are, you know, 0, 0, 1, 1, 2, 2, and 3, 3. And I hope that is clear what it's doing here when I'm feeding in these two lists. But if I do an interlace, I get something different. I get a grid. And I could get 16 vertices because it's taking every element of the first list and matching it with all the elements of the second list. And then the second element of the first list, again matching it with all the elements of the second list. So it kind of interlaces them, or what we call a Cartesian product. Now, if I add Z to this interlacing, it will do a three-dimensional interlacing. It will do it correctly. And I will get a three-dimensional cube, basically, or lattice, or whatever you want to call it, three-dimensional grid of points. So I'm going to use these points to place the cubes at. So I'm going to take the cell prism and then take these 64 vertices and use them as the origin. And then I will visualize what I have done. So I'm going to reuse this topology.geometry. Instead of, you know, seeing the vertices, I will see the cells, and here they are. Now the cells are located, as you can see here, using the bottom surface, and they are centered on the bottom surface. So this is the origin of each one of them. If you don't like that, let's go ahead and use the lower left, and you'll notice it moves and aligns itself nicely with the X and Y axes. Okay, and of course you can change these things. You can, you know, you can make them spread out a bit. Like for example, if I said I want this to be 6, you'll notice that they will spread out, and that's what they are. But in order to build a cell complex, because that's what we are after, the cubes need to be touching. So we really need them to be all one next to the other. So we'll change it back to 3. Great. So now that we have these 64 cells, we can go ahead and build a cell complex out of them. So again, we do Alt spacebar, and we look for CellComplex by cells, and we feed it those, and then we can control click on that. It will take a little bit of time. My computer is slowing down today. I think there's some other task going on. Here you go, and we have now a cell complex. Great. So let's go ahead and get the edges of this cell complex. So in order to get any subtopology, there is a node called topology.subtopologies. So let's search for it. So subtopologies, and you can choose what you would like to see. So in this case, I would like to see the edges. So here are the edges, and again, I'm going to reuse this. I know that there are no polygons here, so I can disconnect the polygons and just simply say I would like to see the edges. It's going to look the same as before, of course, but these are unique edges. There are no overlaps. It's exactly the number of these smaller line segments that you see here. If you count them all up, you'll end up with 300 unique edges. So we'll use that just to visualize our cell complex. But I'm interested in the cells and trying to find the neighbors of a selected cell. So I'm going to go ahead and reuse this. So I'll make a copy of it. And instead of edges, now I'm going to get cells and connect the cell complex to it. So let's see how many cells we have. We have 64, which is, 4 by 4 by 4, which is exactly right. So now we have these 64 cells. let's go ahead and get one of them. We can just do like a list item and change the item number. So I'm going to look for something called list item. And we should be working on level 1 of the list. It's not a nested list, as you can see here. It's a flat list. So feed that in. And then let's see what it gives us. This is the item. So here is a topologic cell out of it. And if I change the index here, I will get a different topologic cell. So let's go ahead and visualize that. I'm going to copy the topology geometry and the temporal view, put them here, and I will color the cell red. So I'm going to go to RGB and say I want just red, exactly like this, opaque red, and feed it the cell. And let's see where it is. Why am I not seeing it? Where is it? First of all, that is a topologic cell. Sorry, of course, because I have not connected the polygon, so it's showing it in edges and they're overlapping, so I'm not able to see it. But once I connect the faces, here it is, it shows up. Sorry about that. Fantastic. So this is the cell, and if I change the index, it will jump around. It will pick something else. There is no order to the cells. We don't know exactly how Open Cascade, which is the engine underneath Topologic, orders these cells. So they're not like in rows and then columns or something like that. No, it's just random, it seems. It depends on how the geometry was created. Okay, so the idea now is that now that we have this one cell, we want to get its adjacent cells, the ones that share faces with it. So like the one on the left, the one on the right, one on top of it, one at the bottom of it, these types of things. So you can get that easily by a node called cell.adjacentCells. So let's go ahead and look for it. So we'll look for the word adjacent, and you'll notice that I have adjacent edges, adjacent faces, etc., etc. So there is something called cell.adjacentCells, and we get again this cell that we have selected, and we ask it for its adjacent cells. Again, if I right click or control click, excuse me, on this one, you'll notice that it's telling me that it found these 4 cells. So, you know, this one, one above and one below. So 4 cells. It doesn't return cells that share edges, only if they share a face. That was a kind of a design decision that we made, that we would like to return the cells that share faces. Right, so let's go ahead and visualize those. So we'll take topology geometry, we'll take this again, make a copy of it. And this time around, I'm going to change the color so that it is yellow. So red and green are 100%. And I will reduce the alpha to whatever, 4.8. And feed it those 3 cells. And there they are. So it gave me those 4 cells. So now I can exercise this a little bit. I can say instead of index 9, I want index 10. And everything gets updated correctly. Sorry about that. Here we go. So that you can find out the neighbors of the cell that you are creating. Now, this is a bit difficult. This is a rendering issue sometimes with Blender. Depending on the order of the rendering, the ones behind translucent objects don't show. But as you can see, this is the actual cell. And the 5 cells are around it, and if you check it here, we have 1, 2, 3, 4, 5 cells that have been found. And that's it, really. It's as simple as that. You know, hopefully this is helpful, and thank you for listening. I will just simply now show you the full definition and clean it up a little bit, as I usually do, so that you can implement it if you would like to. Let me just go through them one more time. I think it's useful to do that, but let me first clean them like this. Adjacent cells, that's fine. right, perfect. So let's go ahead and go through it from left to right. So we created a number range from 0 to 3, and we created 4 numbers, so this would be 0, 1, 2, 3. We fed that into the x, y, z coordinates of a vertex, and we chose interlace as a method of replication. So this will create a 3-dimensional grid matching every element of this list with every other element of every other list. So that gave us 64 vertices distributed in a 3-dimensional grid. We use these origins to locate a prism, in this case a cube, which is 1, 1, 1. And because the spacing is 1, all the cubes share faces. They're touching each other. And we chose lower left as the origin of each of those cubes. Now that we got 64 cells, we created a cell complex out of them by saying CellComplex.byCells. And in order to display this cell complex as a kind of cage or framework, we used Topology.subtopologies, and we chose the edge as the subtopology we're interested in, converted it to Blender geometry, Topology.geometry, and displayed it using a yellow line, as you can see here. And that's what you see here in terms of the cage. We used the same Topology.subtopologies node, but this time we chose to choose a cell out of it, and we got 64 cells. If you count those 4 by 4 by 4, you get 64 cells. We chose a cell at random using list item. So we got list 11 here, or index 11, excuse me, and we got a cell which is here at the bottom, and we displayed that using a red color, Topology.geometry, and then temporal view to display it by color. We took this cell and we dropped a cell.adjacent cells node onto it, and that gave us the 5 cells that are adjacent to that cell. And by adjacent, it means they share a face. As you can see, they share 5 faces, each one respectively. And we displayed those 5 cells using a translucent yellow color. And that is the definition. Again, thank you for listening, and I look forward to making more videos for you.